In Section 5, we're going to cover the theory of orbitals and bonding. This is probably, to some extent, a review topic from Gen Chem. However, like many other review topics, we're going to need you to understand it better and be able to work with it in more detail. The first thing we're going to cover is atomic orbitals. First, what are atomic orbitals? Well, atomic orbitals basically are sort of diagrams of behavior, specifically the behavior of electrons. It turns out that in our quantum mechanical theory, there is a correlation between the energy of an electron when it's around an atom and the space in which it is allowed to exist. So a given electron with a certain amount of energy can't just go anywhere. It has places where it is allowed to exist and more likely to exist. The atomic orbitals are basically the diagrams that show in 3 dimensions a picture of what that 3-dimensional space looks like. Now, where do they come from? Well, atomic orbitals come from math functions. So scientists, when they were developing the quantum mechanics, they came up with functions that showed, that sort of plotted this relationship between the energy of an electron and the area where it's allowed to exist in space. And these functions were called wave functions. Now, we're going to symbolize wave functions with this capital Greek letter psi, and then x, y, and z, because the functions are 3-dimensional functions. They're functions that have both an x, a y, and a z variable corresponding to the x, y, z of 3-dimensional space. So what scientists did then was they took the xyz wave function and they substituted numbers into it for different locations in space. So they said, for example, 0, 0, 0, 1, 0, 0, and so forth. And when they substituted those numbers, they could calculate out a number from the function. So psi of xyz gives a number. We change the x, y, z, we get a different number. What they then did was they plotted those numbers on 3-dimensional space using dots of different size to represent the size of this number. The location would represent the x, y, z numbers. And when they plotted those numbers out, what they got was a shape that was sort of like a cloud in a way. Parts of it were much darker because the numbers were bigger, and parts of it were less dark because the numbers were smaller. But the overall cloud would have sort of a shape. So this, for example, is sort of a representation of what a 1s orbital plot would look like. So this is the psi 1s function. And when we plot the psi 1s function, what we get is a sphere. It turns out the densest part of the sphere is right in the very center, and then it sort of gets weaker and weaker as it goes out. And it turns out that actually the numbers really don't ever go exactly to 0 in the 1s. But instead, they just get so small out here, far away from the nucleus, that we impose a cutoff, and we say that because the number is so small, the electron is very unlikely to be out there. So once the people developing the quantum mechanics had these wave functions and they were able to plot them, then they had to sort of decide what is this telling us? So wave functions relate the energy of electron to its location in space around an atom. There's a 1-to-1 correspondence. So what that's basically saying is if an electron that's around an atom has a certain amount of potential energy, then it will be in a particular location of space. If we change the energy of the electron, the location in space will change. If we change the location in space, the energy will change. Now, how do we know that this is the case? Well, it turns out that the wave function number that you get is actually related to a probability, the likelihood of finding an electron with that given energy at that XYZ location in space. Specifically, it turns out if you square the psi function and then plug in the numbers and then get the numbers out, those numbers are the probability of finding the electron at that particular XYZ location. The bigger the number, the higher the probability. You have to square it because some functions produce positive and negative numbers, and there is no such thing as a negative probability. Probabilities always go from 0 to 1. Each different allowed energy has different unique psi functions. So if we, for example, allowed an energy at 9 electron volts, which is a unit of energy that we use for measuring electron energy around an atom, it might have one psi function. If we had 11 electron volts, that would have a different psi function. So by looking at all of the different psi functions, what we define then is the energies that the electrons will take when they're around that atom and what location they will be found in space. Now there's many different types of atomic orbitals, and I'm sure that in general chemistry you heard about them. There's s orbitals, there's p orbitals, there's d orbitals, of which there's 5 different shaped examples. There's f orbitals. And really, every atom has all of those orbitals. But what we see is for atoms that have very small nuclei, have very few positive charges, the energies of the d and the f orbitals become so incredibly high, the electron would have to have so much energy that probably other things chemical would happen instead. So we are going to restrict ourselves primarily to s orbitals and p orbitals. So the shapes of the s orbitals and the p orbitals are indicated here. We already looked at the s orbital earlier. We see that there would be a function we call psi. It's a psi of s. It's an xyz function. If we plugged in xyz and plotted the numbers as dots, we would get a shape, and the shape basically looks like a sphere. The center of the sphere is the nucleus, and in fact, close to the nucleus, the numbers are bigger, the probability is more dense than far away from the nucleus. In contrast, when we look at the p orbital has a really, really interesting shape that initially can be kind of confusing. When we plot this thing, what we end up with is 2 spheres, roughly spheres, 2 sort of roughly spherical shapes that exist above and below, or left and right, or in front and back. They exist along one of the XYZ axes. So for example, if we assume that the x-axis is the left-right axis and the y-axis is the axis coming out and going back, and the z-axis is going up and down, then this would be a drawing of the p orbital that is aligned along the z-axis. We have a sphere above the xy plane, and we have a sphere down below the xy plane. Now, there's a couple things about this that are important then. First of all, we would call this PZ because it's aligned along the z-axis. There's also a px and a py orbital. So there's actually 3 orbitals, and the electrons in those orbitals all have the same energy. But we're going to see that electrons like to spread out because of repulsion. So electrons are going to sort of fill them one at a time until they get all filled up. Now, the second thing to notice is that if this is the z-axis, this is a number line. And the numbers above the axis are positive numbers, 1, 2, 3, whatever. The numbers below the origin here are negative numbers. And so this P of XYZ is in this region given positive numbers and in this region giving negative numbers. And this is why we need to square the psi functions in order to get the true probabilities. The probability will basically be the square of these numbers. The third thing to notice is that in the s orbital, the highest probability of finding the electron is basically in the center of the orbital at the nucleus. In the p orbital, what we see is at the nucleus, the probability goes down to 0. The number value, if we plug in 0, 0, 0, so psi of p 0, 0, 0 gives exactly the number 0. That means there's no probability of finding the electron there. We have a name for this in these clouds. We call it a node. And importantly, nodes represent a place where the mathematical sign of the numbers goes from positive through 0 to negative, just like they would do on a number line. Finally, it's very important to point out, we can see it right here, that the number that we get out for these psi functions is not an electrical charge. And this is unfortunate. We have these electrical charges and we say the charge can be a positive charge or a negative charge. But these positive and negative numbers do not represent charge. In fact, because they're just locations of electrons, they're always negatively charged. The numbers instead just represent mathematically the number we would get if we plugged in x, y, and z. However, the positive and negative values for these things are going to be important when we begin to try to use them to make bonds. A couple other review things. There's always 3 different p orbitals. They have the same energy. We have a term for orbitals that have the same energy but are different psi functions. We call those degenerate orbitals. It's also important to notice that a given psi function can describe 2 electrons. So there can be 2 electrons with the same energy existing in the same location in space. However, it can't describe more than 2 electrons. So if we have a third electron, that third electron would either have to have a different energy, or if it had the same energy, it would have to have a degenerate orbital available to it, so it could be in a different location in space. What we then do with these things is going to look familiar. Scientists calculate out the potential energy numbers for the electrons that correspond to these orbitals. So for example, for a carbon, which has 6 positive charges in its nucleus, we can calculate out the energy of the electrons in the 1s orbital. We can calculate out the energy of the 2s and the 2p. And what we see is that those energies gradually increase. We can then look at the number of electrons that are in the carbon, and we can start assigning them to an orbital. We could say 1 electron is described by this orbital, another electron described by this orbital. And when we do that, what we find is that the electrons generally prefer to flow down into lower energy orbitals, which means that their energy goes down and they give off energy, and the location where they exist in space is different. So for example, if I had an electron up here in this p orbital and there was a space in the 2s, the p orbital would go from being in this 2-sphere p orbital, it would change into a single sphere centered on the nucleus. Finally then, one last point I would like to make which doesn't appear to have made it in the written notes, is that in quantum mechanics, electrons have very unusual properties. Electrons are very, very, very tiny objects, and it turns out that once you get down to that tiny, tiny size, the natural world has some different rules. One of the most confusing of these, and yet actually very useful, is the fact that electrons, they behave both like particles, as we're accustomed to, and they also behave like waves or like clouds. I find it most useful to imagine the electron being a cloud of negative charge, sort of like a fog. And the fog takes a certain shape, and fog can be more dense, more opaque, or less dense, partially transparent. And that's really the way that I visualize them. So what this orbital is basically defining is the shape of this cloud of electrons. That's going to become useful to think of them that way when we go down and look at how bonds are formed.